Hello students, myself Professor Ankur. I welcome everyone for the gate theory session on analog circuits. This is the third part of our topic of MOSFET, and today we are going to cover an important topic, MOSFET AC model and amplifier. So let's start with now MOSFET AC model and amplifier. So here we are actually looking at the small signal AC model of the MOSFET. The symbolic representation will look similar to the model of the FET. At the input side, we are having an open port and the voltage measured is going to be VGS. At the output side, we are having a current source represented by a value GMVGS and the output resistance between the drain and the source represented as RO or RD. The value normally comes as 1 by YOS, or it will be 1 by lambda times ID, depending on the data, whatever is given. If nothing is specified in the question, we can consider RO equal to RD equal to infinity. So this is representing the small signal AC model of the device. The model is applicable for both D MOSFET as well as E MOSFET. This is corresponding to N-channel MOSFET family. So if I go for the P-channel MOSFET family, the direction of the current source will be reversed. So now let's have a question, and we are supposed to find the voltage gain of the amplifier circuitry shown there. So if you observe carefully, we can see a MOSFET with drain, gate and source, and at the gate terminal we are having the DC battery in the form of VDG, which is represented as VGSQ, and we are having an AC source represented as VI. The output is taken from the drain terminal, which is represented as VO. So when I go for the AC representation or the AC equivalent circuitry, the gate, drain and source is as shown. The input side will be open port, which is going to be VGS, which will be equal to VI. And the output side we are having GMVGS and the output resistance RD. During the analysis, we are assuming that the internal resistance of the MOSFET measured from the output side is very high. I'm considering it as open circuit, that is infinite. So automatically the value of output voltage VO will be the current value GMVGS into the resistance, that is going to be RD. Looking at the direction of current, the polarity of the output will be negative, and that's the reason VO will come as minus of GMVGS into RD. The value of input voltage VI is going to be same as VGS. So when I see VI is equal to VGS and VO is equal to minus GMVGS into RD. So when I get the value of VO by VI, by taking a ratio of VO by VI, you'll get the value as minus of GMRD. Implies that this amplifier, basically it's a common source amplifier and the gain is going to be negative. If the voltage gain is negative, it implies that it is going to be a inverting amplifier. The input impedance measured is going to be infinity and the output impedance measured is going to be equal to RD. Now suppose if I go for the MOSFET CS amplifier with the potential divider bias arrangement, we have already seen how to go for the solving of the MOSFET amplifier for the DC calculation, where we replace the input by the Thevenin circuitry and then you find the value of VG, which will be VDD into R2 divided by R1 plus R2. The equivalent resistance for the gate will be R1 parallel R2, and then you will go for VGS is equal to VG minus IDRS. We use the equation for the drain current. You get the value of ID, and once we get the value of ID, we apply KVL to the output loop, and you land up with the value of VDS. So now we have got the value of ID, VGS and VDS from the DC part. So if I want to go for the AC part, I need to replace the device by the AC equivalent model and then go for the condition where all the capacitors will work like short circuit and the DC battery will work like ground point. So from that we land up with the AC equivalent circuit of the MOSFET CS amplifier. So here you can see the AC equivalent circuit of the MOSFET CS amplifier, where you can see between the gate and the ground R1 R2 present, and at the output end we are having RD. VGS, GM VGS and RD is basically the part of the device. So when I get the value of gain, the gain equation will be minus of GM into RD parallel capital RD. If the value of RD is very, very large, you can take AV value as minus of GMRD. Many of the times when RO or RD is not given, we can consider it as infinity. So we'll end up with the value of AV straight away as minus of GMRD. If the RL is given, the equation will get modified into AV as minus of GM RD parallel RL. The input impedance for the circuitry measured here will be Ri as R1 parallel R2, and the output impedance measured will be ZO equal to RD parallel capital RD. So this is how you try to analyze a circuitry for the voltage gain, input impedance and output impedance. Current gain is never analyzed for MOSFET amplifiers. It is all because the MOSFET is actually having an open port effect at the input side due to the insulation of the gate. And that is all because of the existence of the SiO2 layer. And hence there is no current gain calculation in MOSFET family. Now suppose if I go for the representation of P-channel E MOSFET. So the P-channel E MOSFET circuitry is given here. So here we are having the output at the drain terminal. So we are having a VDD battery of minus 9 volt and then RD of 1 kilo ohm and the output at the drain terminal. The gate is having a resistance Rg of 100 kilo ohm and connected with an input source. The source is having a resistance of 1.2 kilo ohm and the VSS value is 9 volt. And then we are having a bypass capacitor CS present across the source connected to ground. So when we go for the AC equivalent, you will automatically see the source terminal getting grounded, the input side having Rg and Vi, the output side having Rd and Vo terminal. The device should be replaced by the AC equivalent, and in the AC equivalent, we have to ensure that the direction of current is opposite to what we have used in the model of N-channel E MOSFET. Here, now we are looking at the common drain amplifier circuitry. In the common drain amplifier circuitry, you will find that the output is taken from the source terminal across the resistance Rs. At the input side, we are having R1 R2 present. The drain terminal is connected to the VDD point directly. At the input side, we are having the coupling capacitor Cc, followed by the input resistance of the internal source RSI and the voltage source Vi. So RSI is basically representing the internal resistance of the voltage source Vi. When I go for the AC equivalent, the AC equivalent circuitry is shown adjacent to it. So between the gate, drain and the source, we are having open port on the input side as VGS, and the output side we are having GM VGS along with RO. At the source end, we are having RS present and we are measuring the VO across it. And at the input side, we are having R1 parallel R2 between the gate terminal and the ground terminal, RSI and then Vi. If you try to analyze, you can easily say that the value of your VO is basically the voltage drop across RS. So the voltage drop across RS can be taken as the current value GM VGS into RS parallel small ro. So if the small ro is very, very high compared to the value of RS, it will be neglected and you will land up at the equation of VO as GM VGS into RS. And when I take the input voltage for the amplifier circuitry, it will be VGS plus the drop across RS. So eventually, when you get the value of AV, which is VO by Vi, we will land up at the equation GMRS upon 1 plus GMRS, neglecting the effect of RO. If it is present, the equation will definitely consider the impact as RS parallel small ro. Now when I try to measure the input impedance measured from the gate will work as infinity because it's an open circuit. And when I take the Zi or the Ri for the circuitry, it will be R1 parallel R2. And if I go for the last part, that is going to be Zin, it is going to be RSI plus Ri. So automatically, if I try to get the total voltage gain VO versus Vi for the entire circuitry, you will land up at the equation of GMRS upon 1 plus GMRS into a multiplying factor, which will be numerator R1 parallel R2, and in the denominator it will be RSI plus R1 parallel R2. So this is how you get the value of AV. So whatever I've discussed, the same logic is being shown here in the form of a representation. The value of VO by Vi actually can be splitted as VO by VGS into VGS by VI. VO by VGS is already being found out as GM into RS parallel RO upon 1 plus GM into RS parallel RO. As I've said, if the RO is very high, it will be neglected and you will land up at GMRS upon 1 plus GMRS. And if I try to find a total gain of the network, it will be this gain multiplied by a factor Ri upon RSI plus Ri, where your Ri will be actually R1 parallel R2. So this is how you find the voltage gain of the amplifier circuitry.